We have seen the force on a particle that is traveling perpendicular to a magnetic field. We can find the direction, we can find the magnitude. But what does the path look like? If I had a charged particle moving through an electric field, let's say here's a charged particle moving to the right, there's an electric field pointing downward. We know how to calculate that force, we know how to find the direction of that force, and we know what would happen to the path of the particle as a result. It would end up going in a path that looks like this, which is starts with a P. It's a parabola, right? Now, in charged particles in a magnetic field, we know how to find the value of the force. We know how to find the direction of the force. The one thing that we don't know yet is the path of the particle, what that force causes it, what path that force causes the particle to take. Let's do that now. We have a charged particle, let's say, that's negative here. It's going to the right. We'll key this to mean green is the velocity of the particle, the movement of the particle. Red will represent the force on the particle. If this particle is moving to the right through a magnetic field that's directed into the page, what's the direction of that force going to be? We know this, right? From the direction of the particle, this is hand rule for deflection. From the direction of the particle, fingers in the direction of the field, palm points which way? Downward, right? So we're going to say the magnetic force is downward. Well, what happens to this particle as a result of a downward force when it was originally moving to the right? Where's it going to go? Don't tell me the shape of the path. Just tell me ballpark. Where's it going to go? Yep. It's going to go down and to the right. So this particle, now, the next time we look at it, is going to be over here. Now, what's the direction of the force now? We're going to say from the direction of the particle, which is down and to the right, fingers into the page. Force is going to point this way. Force is going to be this way. Agree? All right, where's it going to go now? It's going to go somewhere in between. Thumb in the direction of the particle, fingers in the direction of the field, palm points which way? Kind of up this way, right? What do you notice about A, the path of this particle, and B, the direction of the force? Yes, that's exactly it. This charged particle that's going through the magnetic field will go in a circular path. That is, as long as it's in the magnetic field. Once it leaves the magnetic field down here, it's going to go in a straight line, right? That's a whole other problem. That's a physics 20 problem once it's out of the magnetic field. While it's in the magnetic field, it will go in a circle. Now, we can see that from another point of view as well. The force that's acting on this particle is always pointing which way? Inward, toward the center of the circle. What do you call a force that always points toward the center of the circle? Centripetal force. It's a centripetal force. So we can now use, in addition to the equation that we learned last week for magnetic force, which is still valid, by the way. You guys did 4 or 5 questions for homework on worksheet number 11 using this equation. It's still valid. We wouldn't go back and change the way we did those questions for homework. We'd still do it the same way. But in addition to this equation that we learned last week that is valid, so is this. F is equal to mv squared over r. That's my centripetal force equation. Anytime you have a force that acts toward the center of the circle, a force that causes an object to go in a circle, we call that a centripetal force. Now, there is one more thing that I can do, which is really just a combination of these. The centripetal force causes it to go in a circle. But what is it really that causes the centripetal force? It's the magnetic force. Something always causes FC. FC is never out on its own. It's always caused by gravity or electric force or magnetic force or something. Here it's caused by the magnetic force. So we could, if it's convenient to do so, set FC equal to Fm. As long as the charged particle is in the magnetic field, it will experience a magnetic force, and it will go in a circle, and therefore experience a centripetal force. So we can use the magnetic force, or the centripetal force, or a combination of them to do our analysis, depending upon which one happens to be convenient, given whatever we have given to us. Now, One more quick question before we flip the page and do an example here. What would happen if this charged particle is moving faster? What would happen to the path if this charged particle is moving faster? Remember, everything that we're doing here means it has to be perpendicular, right? All bets are off if it's not moving perpendicular to the field. If it's moving faster and still perpendicular to the field, what's going to happen to it? No, it wouldn't get smaller, actually. Good guess? The radius would get bigger, right? When you're driving your car on the highway and you go around a turn at a high speed, you tend to take a bigger radius when you're going at a high speed, right? The slower you're going, the smaller radius you can take. The faster you're going, the bigger, the wider the turn you need. So that's exactly what would happen here. If this charged particle is moving faster, it would end up going like this. Still moving in a circle as it moves through the field, still going in a straight line after it leaves the field, but it would just be a bigger radius, that's all. Does that make sense? Both of these questions, while it's in the field, we could use any of these three equations. Once it's out, all bets are off. Now, one more little thing before I flip the page, actually. I'm going to star the first equation and the last equation. Not because they're any more valid than the middle equation, but just because it usually ends up being either the first or the last that I end up using. There's no reason why I can't get a question that uses just the middle one. It just seems like I don't. I more often get the first one or the last one, which means that if you're not sure what to do, try the first one or the last one. If it doesn't work, okay, then try the middle one. But try the first or the last one first. Okay? Let's take a look at the example that we have. Example number 3. It says the electron is moving at this speed to the right through a magnetic field that's pointing into the page. What's the radius of the path? What's the direction that it will bend? Well, charged particle moving through a field, we're allowed to use F is equal to QVB. We're allowed to use F is equal to mv squared over r. Or we're allowed to use the combined equation, FC is equal to FM. If you're looking for radius, you're usually going to use the combined equation. There's nothing wrong with trying one of the other ones, but you're usually going to end up using the combined equation. So let's try that first. If you're looking for radius, or if you've got the radius, probably going to be FC is equal to FM. Let's say mv squared over r equals QVB. We can actually cancel out one of the v's here. Do you see that? V squared on one side, v on the other side. One of the v's on each side disappears. And we're solving for r here now. Take the r up by multiplying. mv is equal to q times b times r. And then take the qb down by dividing. And then we sub our numbers in here. The mass is the mass of the electron. And V is 4 times 10 to the 5. Q is 1.6. And B is 2.5. When we do this, we end up getting 9.11 times 10 to the minus 5 meters. So it's a pretty tight turn, pretty tight radius, 10 to the minus 5 meters. Which way does it bend? If the magnetic field is this way, and the electron is moving this way, which way does it bend? Thumb, fingers, palm points down the page. It would end up going in a circle, kind of like this, curving down the page. Is that okay? I would like you guys to have a look now at worksheet number 12. We'll give you a little bit of time to work on those. Questions on worksheet number 12, 1 through 5. And then either later today or first thing tomorrow, we'll take a look at a situation that uses this, right? A practical application of charged particle in an external magnetic field.